And that gives a magnitude and a direction because there's an I and a J telling which directions those amounts are going. And in scalar form, you can use the formula of your resultant force. And this is actually just the Pythagorean theorem, right? Because you took one leg squared plus another leg squared, and when you take the square root of it, it gives you the magnitude of the hypotenuse. Use sine or cosine, or tangent, actually. So, any preferences on how to find that angle given these two legs or the hypotenuse?
You never use values that you calculated in the problem.
Slightly more inaccurate, correct. So if you want to use these two, then we have the opposite leg and we have the adjacent leg. And if you think about sine equals opposite over hypotenuse, right? Remember your...
So that would be tangent?
Right. It's tangent because what we have is we have an opposite and we have an adjacent. So you'll set it up as the tangent of the angle that we're looking for and over again. So very important lesson of the day. A few other things to know about forces. This is in your book. And again, if you don't have your book, I will get you a copy after class. Transmissibility. What transmissibility means is that a force can move along the line of action that it's acting on. So if you have a force here, that will be the same force there as it is here. You can push something from one side, you can pull it from another. The effect that it has on the object is the same. And it can always translate along its line of action. This really comes into play when we get to trusses in time, yeah. Non-concurrent means just that they don't act at the same place, right? So you may have one over here, and if we're talking about this point, and you have another force over here, those are non-concurrent because the point that you're looking at, they don't happen at the same place. Now, if you follow these along their lines of action, there may be a point out there in space somewhere where they cross, but if we're talking about this point, they're non-concurrent. That also will come into play very quickly whenever we learn about moments. And finally, when you're dealing with beams, most of the time you see parallel forces. Parallel forces just means that they all act parallel to each other. So, last but not least, some examples. So here we have a scalar value with an angle to show where it's at, right? We want to convert these into a vector with I and j components. So what you want to do whenever you get these situations is you want to think about this as a triangle. And on that triangle, the 50 kip force is going to be the hypotenuse. And if you want to think of it like a length, like the length of the hypotenuse is 50 kips, that's fine. What we're looking for, because we want the components, we want the x and y. So, katoa. Right, you want cosine, because you know the hypotenuse is 50, and you want the adjacent side, and you know the angle. So you'll write, which is 50 kips. And then you just use algebra. You can solve for fx, which would be 50 kips times the cosine of 30. And you plug that in your calculator, and you should get 43.3 kips. Make sense? And if you want to find Fy, now we're talking about the leg opposite of the angle. So we're going to use 25 kips. And so what does that really mean? That just means that instead of writing this force as 50 kips at 30 degrees, that means you could also write it as 43.3 kips in the x direction and 25 in the y. So those will have the exact same effect on any object placed at the origin. And when you can get things in x and y components, it makes it a whole lot easier later on. And it all goes back to a triangle and using sine and cosine, tangent, and all goes back to trig. Now, there's something else that you might see. You may see a force of, say, 75 kips that's on a slope. A slope that has a rise of 3 and a run of 4. And I always like these because instead of using sines and cosines, I think these makes it a lot simpler. Huh?
Does that make that 3, 4, 5?
It does make it a 3, 4, 5 triangle. Remember how we talked about right triangles? And there's 3, 4, 5s and 5, 12, 13s and 12, 24, 25s, and there's all these kind of common right triangles. 3, 4, 5 is one of them. So you know your components are gonna, one is gonna go up, your y component, and the one in the x direction is gonna go to the right. The amount that they go in those directions is always going to be equal to, for the component in the x direction, it's going to be equal to the resultant force, or the force that's of the hypotenuse, times, it's going to be a fraction, and for the x component, you're going to look at the x part of the triangle, which is 4. So you're just going to take 4 over the hypotenuse of 5. And that's going to be the amount of force in the x direction. So in this case, it's 75 times 4/5, which is 60 kips. And for the component in the y direction, you're going to take the force, 75 kips, times the piece of the triangle in the y direction, so this time 3, over the hypotenuse. But I always like that way better. Everybody understand where all the fractions came from, how to find a hypotenuse, common right triangles, all kind of stuff we talked about last time. And what that means is you can write the force as one force on this slope with 75 degrees, or 75 kips, or you can write it as 60 kips in the x direction and 45 in the y direction. So, on the point where these originate from has the exact same effect on that point, whether it's 75 on that slope or 45 and 60 perpendicular to each other. And the next part. So what if you have two forces together here and you want to replace both of those with just one? And it asks for it in vector and scalar form. So I want to get rid of those two. I want to replace it with a single one and tell where it's at. Well, what you're going to do is you're going to take each one of these and break them each up into x and y components, and then you're just going to add up the x components, add up the y components, and then put those back together as one force. So we'll call this force number 1 and this force number 2. So for force number 1, again, you want to think of it like a triangle here. And you're going to get this x1. And the same thing on number 2. You're going to think of it like a triangle. And you're going to get a fx2 and a fy2. So for force number 1, to get the x component, this is a 10-degree angle, and the x component is opposite of that angle, so we're going to use,
Which one?
for force number 1, to get the x component that's opposite of the angle.
Opposite adjacent.
Tangent.
Opposite would be sine, because we know the hypotenuse, right? Remember the force is the, yeah. So when we find the opposite, we'll be finding the x component. When we find the adjacent.
Okay, so I'm rolling. Oh, wait a minute. Try it on the script right here.
Hey, Paul, one question. You want us looking at that or you want us looking at the camera?
Go look at it.
Camera's not here.
Okay, I'm rolling.
So for concrete class today, what we are going to do is find the compressive strength of a concrete cylinder, and that's what this machine will help us do. So we have our cylinder in place. We're going to start applying the pressure, and it's going to be read on this dial. This one can go up to 30,000 pounds, and believe it or not, it's going to take more than that to break the cylinder. Once we get the total amount of force applied, then we'll divide that by the area of the cross section, and that'll give us our total strength in pounds per square inch. So let's get started.
Me, go back to where you said, let's get started again.
Okay.
I want to change the camera a little bit.
Granted, this is plastic, and we don't know how strong it is, but we'll see what we can do.
Okay, so back up a little bit in your speech and then.
Oh, that's wrong.
Okay, I'm going to start on.
Okay, yeah, and this isn't going to move because this is plastic.
Oh, okay. Well, you know what?
You can take a shot at this, and then we can move it up.
Let me see what's in here. Let me see what's in here, because this may.
Okay.
So what now? Start over.
Not all the way over, just maybe the last two sentences before you bend down.
Let's get started. How about that?
Okay. So we'll get a total force applied, and then we'll divide it by the cross-sectional area, and we'll get a total compressive strength in pounds per square inch. Let's get started. Okay, now the gap is closed, and it should start loading. Oh, it's actually over here. It's moving. Cracking in here.
Oh, is it?
Yeah.
Okay, I want to be sure to get that.
Yeah. You can see we're getting up to almost.
Good. Let me just change my angle. I'll have you kind of. So, like, take it from, like you're down there cracking it, and you get up and hook it.
So you can see that it's now cracked, and we had to put 30,000 pounds of force on this cylinder to crack it. And what that means for the compressive strength is you can take 30,000 pounds and divide it by the cross-sectional area. This is a cylinder, so it's round, 6-inch diameter, gives you an area of 28.28 square inches. 30,000 pounds divided by 28.28 gives you a compressive stress, or compressive strength of a little under 1,000 psi.
Yeah, I've kind of put it back together and pull it apart like you did. Yeah, I mean,
Easier said than done.
you don't,
Yeah.
Ready? And you can see this is how it breaks. You can also see what this mix was made out of, because you can see the little grains of sand on the inside. And that was the small aggregate in this mix.
okay, yeah. Okay, do that one more time. Just talk to him a little bit about it.
Okay. You can see the grains of sand inside here. That was the small aggregate in this mix. So a lot of times when you break, you can tell what they're made up of.
So what is all in the mix?
In this one, it was just Portland cement and water and sand. We do several mixes though. We're gonna have one of just Portland cement and water. We're gonna have one with sand aggregate. We're gonna have one with a larger 3/4 inch aggregate.
Which one's the strongest?
3/4 inch should be, but once you break them in the machine, it'll tell you.
Okay, ask her that question again.
Which one's the strongest?
The 3/4 inch large aggregate should be the strongest, but when you break them in the machine, that'll tell you. And loads up to 250,000. So we'll open the valve. Almost there. Okay, it should start moving if you're ready. You can see the needles start to move as it starts to apply the pressure. It's up to about 3,000, 4,000 pounds, 5, 6, 7, 8, 9, 10, 13.
That's all on PSI.
This is in pounds, and then to convert to PSI, you'll just divide it by the cross-sectional area in square inches. Oh, and there it went. So you can see it broke at about 25,000 pounds. And that was its yield point, which means that it's not going to take any more load. And so any more pressure that we apply is just going to make it crack and deform more, but it's not actually going to carry any more force than what it did. And you can see the cracks getting bigger. There's more and more deformation, some spalling over here. But 25,000 is all the force it can take. Yeah. Yeah, you want to?
Yeah.
It's just going to keep falling apart.
Bridge flap.
So why does it start sprawling like that first?
That's just the way it breaks. It just starts falling apart. Usually there's imperfections in the surface, and that's where it's going to start to want to break first.
Is that all it's gonna do?
It probably will keep going. You can see after the edges fall off, it doesn't have as much area to load anymore. So it's just going to keep breaking what's left.
Just falling apart, crumbling.
Yep.
Keep on going.
You get over here,
Look at
Mikey.
somebody's eyes.
We can release the pressure on it though.
Cool.
Yep.
I'm gonna give it a good snort.
And it can break around the pieces of sand and break around the aggregate. Sometimes it breaks through the aggregate, but usually it's the bond between the paste of the cement and the little pieces of aggregate in it. And if that bond is strong enough, that's what gives the concrete its strength. So you put larger aggregate in, as long as it's bonded the paste to the aggregate, it should give it more strength.
Okay. Sit over here and do this all day. That's the bigger piece.
Took a lot out of it.
Rex, do you want to leave the fluorescents on, or do you want to turn it
Let's
off?
turn them off and see how it looks.
Got some curly fingers, no. Just playing.
Time you're ready, I am rolling.
Okay, Michael Hamilton, right, 21,
Yes.
Tulsa.
Correct.
So, let's just say you met me somewhere out off campus, and I said, well, what are you going to OSU IT for? And how would you describe what you're doing?
So I go for civil engineering technologies and learning about pretty much structures, statics, the strengths of materials, of concrete, reinforced steel, the design pretty much all the blueprints to everything.
So is this pretty much like, why would you want to go into the field, and what is it appealing to you about it?
Most appealing to me is getting a degree and making a lot of money when I get out. So that's everybody's goal pretty much.
And civil engineering, what kind of jobs would you try to get? What would be
Pretty
like the ultimate?
ultimate, probably just having my civil engineering, being an engineer. That's my ultimate. I want to be an engineer. I mean, you find anywhere being an engineer, they make good money.
Huh?
Can I feed him?
Yeah, because I'm
Licensed.
licensed engineer.
Okay, say that again, like what job do you want to get when you graduate?
I would like to be a licensed engineer, head of a company mostly, just up in the top where, not the bottom.
Well, why OSUIT? There are a lot of places you could get a degree. Like
I've heard that actually most of the people that go to school here are more sought out by bigger companies because we're a hands-on school, not a school of 100 people tell you just to read this and come back next class period and have all this paperwork done. More all hands-on, smaller classes, better teacher, student, associate, and like,
ratio.
yeah.
Well, what about like?
Tracy, wait a second, I'm getting some kind of, but I wasn't.
Okay.
Oh, I didn't hear.
I
Yep, I didn't hear that beep.
Okay.
Okay, so now, so you want to be an engineer, a licensed engineer. Why OSUIT?
Because the school's more of a hands-on technology place where you all hands-on instead of like a school that's where class of 100 where they tell you to go read this and do the homework and come back next week. These are the teachers are right there with you, helping you all the way, showing you exactly what to do, and it's more of a smaller class and you learn more.
And you actually get to use the equipment.
Yeah, pretty much use everything that you're going to be using out on the field, not just trying to learn it all in books.
And the problems, it's like you were doing today in statics are pretty complicating looking on paper, but since when you see them in real life.
I'm sorry, stop just a second again. Can you cue up his
I
monitor?
saw that monitor real quick.
What was that question about that? Esme?
Well, like, how she was talking about the force, maybe in statics, or measuring, all that, but you actually saw it
Yeah.
happen in reality. Does that make it easier to understand?
Yeah,
It's
more of
really
a-
complicated.
Okay. More of a gotta see.
Yeah,
What is
see
it?
it.
Visual learner. There you go. I was trying to think. I know I'm probably all red right now. I'm the type that gets all red when I get.
No, you're
No,
fine.
you're not.
Okay.
Feed him the monitor.
Dang.
Just have,
Start that one again from the top.
yeah, I really like that one.
The world will always need civil engineers. Roads,
Okay.
bridges, buildings.
Yeah, I like what he said too. I'm rolling.
If I remember that.
So when you see buildings all over the place, and like, you see them in a new light now.
Yeah. Every time I look at a new building, I don't just see the walls, I see the structures behind it, like the frames, like the support columns and everything. I just look beneath it. Pretty much like I see the blueprint in my head about it, not just the walls.
Good. And then, what about when you came here to go to school? It's a good, how's the campus life as far as like, is it pretty good?
Campus life is very great. We have flag football tournaments, we have dodgeball tournaments, we got everything. They got a good workout facility too, but just everything around, all the students are great, real nice, and teachers are excellent. They're real nice, not like the teachers that are kind of in high school that don't care about you. These ones actually care about you, hoping you get out on the field and get a good job.
Great. That's good. See, that was easy, wasn't it? Did you get your other degrees here too?
Uh-huh. Yeah. I stuck with one degree, but there wasn't that many teachers that qualified to teach certain classes. So in order for me to keep my scholarships and
Or, either going back to school
Yeah.
or, and kind of a continuing education
Uh-huh.
aspect's pretty good to point out. Everybody around here's not.
Yeah, and
Fresh
again,
out of high
whenever you
school.
hear
Yeah,
Tracy ask you a
and-
question, you can reach in and jiggle.
Yeah, well, it popped up with the installation.
Yeah, I see that. Is it going now?
It says it's installed.
yeah, I'm not your average
Maybe we'll
age
switch to a different
18, 19-year-old
We've
student.
talked to, there's That's one of the great things about this campus. But I thought one of the best things is that there's a daycare on
Yeah.
campus.
Yeah.
Which is, you know, I mean, there are a lot of people that wouldn't be able to go to school here if they didn't have that daycare.
Yeah.
I came and did a video and brought my little boy, put him in that daycare so I
Well,
could,
that's good.
yeah.
Oh, okay.
Good for you, Swan. Okay. We're all with you.
Okay, Lenisa, so you're kind of a returning student. Kind of give me your history, just a little bit in a nutshell, you know, that brought you to this point.
Actually, I've been going to school here for about 2.5 years. I started out with my precision agriculture technology degree, and I just kind of continued from there and pursued other degrees along with that. I figured if I fell back onto something, I'd lead to something else. Then I decided to go ahead and, after I graduated out of that, decided to go and become a civil engineering or take the classes in that.
Why do you like that?
Well, I like the hands-on. I like the, I've always been interested in knowing things about the soil combustions, the compact soils, with the buildings, the cement combustions, so how thick and how, you know, the designs of it. And then I'm always curious, I always have curiosity about the bridges and why they crack and how many pounds, and that has a lot to do with the statics class, and eventually we'll learn into the hydraulics.
So is this going to be the last one, or are you going to keep on going after that? Are you going to get another degree, or do you want to be like a licensed civil engineer?
I want to be a licensed civil engineering, but who knows, I might become a master's, you know, go and pursue my degree into that same field. I really like it, so it depends on, I guess, what courses are available and where I can pursue them.
Can you kind of talk about how the hands-on aspect is so big here at OSUIT, and just talk about how you're so much better able to understand these problems when you see them actually happen?
Most people are, some people are good at doing paperwork, but I myself, I come from an uneducated background family-wise, so we did everything with hands-on. So in order for me to combine both of them, that was the best for me. So I really enjoy the hands-on experience.
And you know, you've been here 2 years, so you obviously like the campus. I mean, can you kind of just talk about how, you know, you see, you know, maybe the people that you're in class with and everybody, the teachers are really helpful. What are 5 great things about OSUIT that you can list off?
Actually, I like several different experiences. I really like the small classes where you get to know the teachers, and after a while, then you start getting to know them one-on-one and getting to know how they are. I also like the tutoring with one another. You're getting groups, and you know, more experience that way. You gain more of a knowledge. That's my opinion. There's just different activities. I used to be on the Student Senate, different functions going on at all times, and you eventually get to know one another and start buddying up with others and making your classwork better.
So what would be your dream job then after leaving here?
I haven't really decided on that at the moment. My fulfillment is to finish my education. And I'd like to go ahead and finish my bachelor's and then see where I pursue from there. But I do have goals in the future to go further ahead.
Great. Well, good deal. That's great. I think
corner, then you look for the evidence of the original corner, and you can reestablish that from those references. And so when you're doing a survey, you operate from the original monuments or a perpetuation of the original monuments. And did anybody see where I set down my?
cool remote you have there.
Oh, pooh. And so when you're surveying the public lands, you walk in the footsteps of the original surveyor. Like I say, you try to find the original corners. If you don't, then you want to use properly restored corners, and you may be called upon to properly restore those. Now, if you come up on a monument other than that is evidence in original field notes, you may accept that, but you shouldn't accept it until you verify that that is in fact a perpetuation of an original monument. Now, there is an exception to that, and it's a little iffy. Sometimes a surveyor would have set or reestablished a corner, not in exactly the same place, but over time it's been used time and time again, and so it has been accepted by popular common report. Okay, now how do you go about restoring corners? Well, we could talk about an hour or so on that, but the methodology on restoring lost or obliterated corners is found in the Manual Instructions for the Public Lands of the United States, which is published by the Bureau of Land Management. The original government surveys were done by the GLO. Some people think that's a government land office. It is not. It was a general land office, and that is a half-inch iron pipe located at that particular section corner. And we go over to the other corner and see that we found a GLO stone, General Land Office stone, at the southward corner of Section 5. So there we've referenced the existing corners that were the basis of our survey. If you're working within a platted subdivision, you need, same thing, walk in the footsteps of the original surveyor. And when you get into a residential or commercial subdivision that has been platted and pinned by a surveyor, there's a very good chance that you're not going to find the pins, particularly in residential subdivisions. Why? Well, the surveyor has set the pins when he was doing the survey of that property, but ultimately, other people come in. Someone may have come in and could have been the builder, came in and graded a pad to build a house, may have very easily torn out the existing monuments. Guy comes in to build the driveways. Once again, he's using a grading machine and doing all stuff. Very possibly you're going to use those. So on your survey, in this particular case, you show what the found pins were, and here I show an open circle and say it found 3/8-inch iron pin, typical. So anytime you look at any point on that survey that has a circle that's open, we're telling you that that was found in the field. And then we show right here a solid dot which says set 1/2-inch IP or iron pin. That's surveyor language, found and set. Okay? Also in your survey drawing, you've got to show evidence of inconsistencies. And an example of that, we look right there. We show that the surveyor found 2 original monuments. He found an old iron rod, and he also found a 5/8-inch iron pin noted as cap number 1324. Well, this surveyor, in the performance of that survey, had to analyze the information he found in the field, and upon his analysis, he made the determination that that 5/8-inch iron pin was the original monument, and that old pin was located, and you need to show the location of the pins that you didn't locate was 1.3 feet east and 9/10 of a foot north of the pin that he accepted. Other things that you'll need to show on your survey is overlapping descriptions. If you have a description, which you will have for your survey, you lay out your survey according to that, but the adjoining survey may have been performed on a description that was not in agreement with the descriptions you had. We as surveyors express our opinion to what is a proper location of that property. If there's a disagreement between two property descriptions, that's a dispute that will be resolved by the courts. Boundary lines, if there's differing boundary lines, you want to show those. If there's hiatuses, departure from any standard in survey. Okay? Line and directional changes. In the course of your survey, you're going to have to produce a drawing that someone can look at and see. I have an 83-year-old mother, so. Hello? But you need to show the changes in the direction along your property line. And if you look up here, our example, you'll see we're showing a bearing of north 0 degrees, 58 minutes, 43 seconds, and its distance. Then we show the bearing and dimension here, but then we go into a curve. Now, curves are probably one of the biggest sources of misunderstandings in surveys. Up until about a year ago, we were required to show 3 points or three curve, the chord bearing, and the chord length. The angle is optional. Okay, now, something I do and most surveyors do is when you perform a survey and you generate your survey drawing, what I measured in the field, I called it measured. Some people put survey. And then underneath that, I showed the record bearing dimension. And in my particular case, I say it's plat number 6065. Some people will just put by description. Either way is acceptable. Up until a few years ago, abstractors went crazy. They could not understand why we could not measure exactly the same bearing and exactly the same distance that the previous surveyor could. Fact is the technologies have changed, and on a day-to-day basis, there are effects upon your measurements, which can be temperature corrections, heat waves, that sort of thing. Plus, we're using more sophisticated surveying equipment today than we did in days gone by. Cardinal rule surveying, walk in the footsteps we physically measured, and that's okay. Another way of measuring angles along property lines is to use angles rather than bearings. It's not a very common thing in the state of Oklahoma, but it is something that you'll see particularly in meets and bounds states. Up here, and also I told you I had vertical lettering for what, and then the two property owners get together and say, well, we transferred this property to Smith from Jones, but when Taylor transferred the property, his intention was to do this, not this. Doesn't make any difference. The only documents that will be considered in that court decision is the written words of that description. So once that description is reduced to writings, we can't change it. Okay, easements and rights of way. If you're dealing with platted property, subdivision plat, it will show you what all the easements and right-of-way dedications that were transferred by that simultaneous conveyance. A subdivision plat is a simultaneous conveyance. That means that you didn't write a new description for every parcel in that subdivision. You have a description of the outside boundary of the property, then you have all the lots and blocks shown, and by virtue of that, you show all the street right-of-way, you show all the new easements that are created, and by virtue of that one instrument, it is all simultaneously conveyed. Very clean, easy way to deal with that sort of thing. So if you're working with a platted property, that's how you deal with it. It's provided to you on the subdivision plat. As you can see up there, we show the building line, utility easements, and here we're showing a 33-foot statutory right-of-way. Now, what is statutory right-of-way? Well, this is Oklahoma, land of the red man, right? Every section line has a roadway easement that is dedicated by Indian treaty, but they're not all uniform. Different tribes had different rights of way that they granted. In the majority of Tulsa County, the right-of-way granted on each section line on each side is have 2 rods dedication. How do you find out what that information is? Well, you can go to the Oklahoma Society of Land Surveyors website, and you can download a map that shows you county by county what those right-of-way dedications are. Now, if there are easements or rights-of-way not shown on the subdivision plat by Oklahoma state law, those must be furnished to the surveyor. I just thank God for that requirement, because if it wasn't for that requirement, there are states that if you're doing a survey, you have to send someone down to the courthouse and research all those records to find all of the encumbrances, the easements, the rights-of-way, mortgages, all that kind of stuff. In the state of Oklahoma, we're relieved of that. Okay, on corner monumentation, when you're doing a survey, you're going to locate pins. And what you'll do in the course of that is you're going to confirm the existing monuments. If there are monuments that are missing, well, you'll take that information back to your office, you'll analyze it, then you can go back and reset or set those missing monuments. Some surveyors have the capability, technology-wise, to make those computations to do it in the field. Now, sometimes you can't set
We might want to do that again.
Yeah, can you
I like
close
to-
it back up and then,
Wait, hold on, just a second. One thing's over here. Just kind of-
oh, okay. Okay, you ready for them to go?
Yeah.
I'm ready.
What are you going to do when you open it? Are you going to take it out?
Guess take it out.
Okay.
Now, once you get the instruments out, go ahead and take the boxes and set them in the back.
Wait for the red one.
Okay. Are you gonna open the red one?
Where are you?
Okay.
You never watched Marcus Stewart? You never see how he does it with his hands? Golly.
You'll put that together for me. Okay, this instrument you see us putting together right here, guys, is about $25,000. About 10 years ago, when we first started using, or it's probably longer now, lose track of time, to get in a GPS surveying operation cost you about $100,000. Okay. I'm going to get a drink of water. Worse about, I give presentations, professional organizations, and forget. And so far, I haven't said anything bad about somebody that. Okay, are we ready? Okay, guys. During the course of this class, this are some of the surveying instruments we're going to use, not all of them. But this is a transit or theodolite. It measures both angle and horizontal and vertical angles. It does not measure distance. When you use this type of surveying instrument, in order to get distance, you can either measure the distance by using a surveyor's tape or chain, or you can measure distance by using a stadia rod. And I'll explain that later on in a class on how to measure distance by stadia. It's kind of a methodology that has gone by the wayside. Now, a more advanced instrument is a total station surveying instrument. This is a Topcon GTS 212, and this measures angle digitally. And I forgot to tell you, on this one, when you're measuring your horizontal and vertical angle, you're reading those angles by use of a vernier, 2 scales side by side. And it's not as nearly as easy to use as this. Now, with this particular surveying instrument, when you look into it, you will see, not when you look into it, but when you're measuring angles, on this screen right here, you will see what the horizontal and the vertical angles are digitally. Makes it a lot easier. Now, also in conjunction with this instrument, instead of having a surveyor out there holding a plumb bob or a range pole and you measure a distance to it, we'll take a range pole, and on the top of this range pole we have a prism. And this instrument fires a laser beam that hits that and bounces back and tells you what the distance is. A lot easier, a lot more accurate than surveying using a surveyor's tape, a surveyor's chain, or stadia. Matter of fact, stadia measurements, you know, you're looking at a 1 foot accuracy. You would not use that for a boundary survey measurement. Really made a surveyor's work a lot easier. Now, in conjunction with the transit and the level which we'll talk about here in a little bit, you have to record your data in a surveyor's field book. You have somebody keeping notes, writing down all those vertical and horizontal angles and the distance that you measure. With this particular instrument, you don't have to do that when you're using the data collector. Now, initially in this course, we're not going to be using a data collector. We're going to be using a surveyor's field book, but after we've learned how to do that, then we'll use the data collector. Now, what a data collector is essentially an on-board computer that records X, Y, and Z coordinates of all the measurements that you take, and the operator, all that information has dramatically reduced the time to take the information from the field and put it into a drawing form. A really experienced surveyor working with a really experienced drafter or technician in the office can just almost have a complete survey by downloading it directly into AutoCAD and then adding a few things to it. This is done away with field book. And when they first started doing this, a lot of surveyors were very adverse to it because they say we no longer have a field book. And a field book was a legal document. You're not allowed to make erasers in a field book or take pages out if you're state of the art, and things are only going to get more automated. Now, this instrument right here, tiny little thing, is a level. Now, a level only measures elevation. It does not measure horizontal angles. And how you measure those elevations is you set the instrument up and you backsight to a benchmark. Now, a benchmark is through the sight on that. You're looking at a stadia rod, and wherever your crosshairs, that tells you how far you are above that benchmark. And when you're doing levels or measuring levels, and that's one of the things we're going to be learning in this class is how to do differential leveling, we're going to set up midway between 2 points, and we'll take our measurements. Backsight to the benchmark, foresight to the new position where we want to determine where what the elevation is. And the surveying instrument that so many of you have been excited about is GPS, which stands for global positioning satellites. There are 25 satellites in space sent up by the U.S. government. Those were originally set up for military purposes, but they have now made those accessible by surveyors. And on a GPS system, you have one part of it that sends a signal up to the satellites. You want to have at least 3 satellites that you're recording the information come. It'll send back information to you and very accurately tell you what the X, the Y, and the Z coordinates are. It is just a tremendous step forward in surveying technology, but one of the challenges of it is you do not have the ability to very quickly check to make sure that all your locations are correct. When you use either a total station surveying instrument like this or use a transit with your field notes, you can run around that property and see how it closes. And very often, or sometimes I should say, you find that there's obviously been an error made. You can track down those errors. When you're using GPS and you only take one sighting, you're not exercising the ability to check yourself. Surveying instruments are only going to get more and more sophisticated. Probably in the next 10 years, surveying instrument will be such that you'll have a rod like that, have some kind of instrument on it, and you can go surveying by yourself. Hopefully, we will never get to where we're surveying by ourselves because of the environment we work in. For safety issues, I think you should always have at least 2 people in your survey party, particularly when you're out in the woods, because you can get injured, get bit by a snake, you could fall down and break bones or something like that, or if you become a tenured surveyor like myself, you might have some other malady. But surveying is constantly on a change. The equipment that we have is getting better and better, but we always have to keep in mind the basic principles of surveying. Walk in the footsteps of the original surveyor, do proper surveying. Remember that sometimes a $10 tool put in the right place will give you better data than a $10,000 total station surveying instrument. Any questions we have, class? Well, it's time for class to be over. I appreciate your attention, and we will see you next Wednesday wearing your OSU paraphernalia. I'm going to go to the field next time. Thanks, guys.